Welcome to Lecture 21A, entitled Definition of Circulation and Flux and Geometric Interpretation of Divergence and Curl Operators. So this is very new material and will take a little bit of time to digest, so I'd go through this video and the accompanying reading material very carefully. This lecture will be taken from sections 1.8 and 1.9 of Reading Assignment 4. And the main objective of this lecture is to understand the meaning of circulation and flux. So it gives you some intuitive feel as to what these different concepts represent. And so the main concepts and visualization skills that you'll get from this lecture are the conventions for defining tangent vector and normal vector, which is more or less a repeat of some of the things we've already discussed. The notion what is circulation and flux, but more from an intuitive point of view. The definition of divergence and how to compute the divergence of a vector field, and the definition of curl and how to compute the curl of a vector field. As usual, the second slide is more or less a summary of the material to follow, so we'll just skip over that slide. All right, so the first thing to do is to try to understand a vector field in 2D because it's simple to graph, and the basic ideas regarding what we want to convey here can be explained quite nicely in 2D. So what I've shown here are three pictures. The one on the left, I basically have shown fields shown in black, which I call an F flux, which is X and Y. It's a radial field and it's pointing outwards, and it appears to be emanating from the origin, from the center. And I'm calling that a flux field. Flux meaning it's something sort of moving outwards or moving inwards. The middle diagram, I have a field F circ, which basically means that I have a field that forms a closed pattern, a closed circle. And I'm going to define this particular example as having the vector field of minus yx. And the third one on the right is a superposition of both fields drawn together. It forms what appears to be a spiral. And so the vector field in that case is a spiral. So one on the left is radial pointing outwards, one in the middle is forming a closed circle, and the one on the right forms a spiral. Over top of this vector field, I'm basically putting a contour of radius r for all three cases. And I'm going to be traversing the contour in a counterclockwise direction. And so I can assign a tangent vector that's tangent to the contour, which will be capital TDS. T is a unit tangent vector. And then according to convention, the normal to the contour will be pointing to my right if I move in a counterclockwise direction. So the normal vector will be n subscript s ds, n subscript s being a unit vector that's normal to the contour pointing outwards. And I've done this for all three diagrams. Same contour, same radius, same definition for TDS, same definition for NDS. So that's basically my starting point. Now the contour basically is a circle of radius r, and I'm going to need to parameterize it because I'll need the tangent vector and the normal vector to the contour. So for parameterization purposes, the simplest way to parameterize a circle is by saying r times the vector cos t sine t, and the direction is correct. If you basically advance t, you'll be moving in a counterclockwise direction. You want to complete a full circle, and therefore the range on t is between 0 and 2 pi. You derive the tangent vector by taking the derivative of the position with respect to variable parameterization variable t dt. And so the expression that you see here is the tangent vector. The normal vector would be just normal to this, which means if you took it and the dot product with respect to TDS, you get 0. And so the appropriate normal vector, which is pointing outwards, would have this form. You can confirm it. If you basically plot this for a couple values of t, you'll find that the normal vector is pointing outwards from the contour. Okay, so this is actually the convention, and I just want to remind you of it. So here are the three different fields. This appears to be a radial field pointing outwards. We'll call this a flux field. This is a field which appears to form a circle, so we call it a circulation field. And the total field is the superposition of two types of fields. Turns out there are only going to be two types of fields. Any field can be described in terms of a field having flux-like properties and a field having circulation-like properties. Okay, so we're going to compute for this particular example. We're given the field vectors, we're given the contours, we're going to calculate the circulation and flux in 2D for the different combinations. Okay, so you have the circulation is by definition to take the vector field dot TDS and integrate around the loop. And in this case, we're just going to take the circulation vector and do this calculation. So going from the previous slide, we know what TDS is, it's this. And the field vector for circulation, again, because it's given as minus yx, we parameterized x and y in a specific manner, and so we have to make the appropriate substitutions. So we have minus sine t cos t. If we basically take the dot product, integrate, we have 2 pi r squared. So that means if you take a vector tangent to the contour, which happens to be in the same direction as the vector, which in this case is circulation vector, then we expect that this integral will produce a number. And this number represents the strength of circulation. That's all it means, something related to the strength. But it's interesting though, it seems to have something in here called pi r squared, which is actually the area of the loop enclosed by the contour. This is going to become important, but we just mention it here. If I take that same field now and instead do a flux calculation, that means I use the normal vector, I'll end up basically with a value of 0, which means that the flux for a field which has got pure circulation is 0. All right, so that's interesting. It means that these two types of operations can give you information about the nature of the fields. A pure circulation field has no flux. All right, let's turn it the other way around. Let's take the circulation again, but this time let the field be the flux field, and we integrate around closed contour. In this case, of course, the TDS field hasn't changed, but now this is the flux field. If you do this integration, you'll end up with 0. Alternatively, if you now take the flux calculations, but the field is the F flux, then this gives you 2 pi r squared. And again, mysteriously, this pi r squared factors in here, which represents the area bounded by the contour. All right, so just a quick reminder, the fields, what are the units of the arbitrary field F? Well, this is circulation, this is measure of length, and so F is a measure of circulation over meters. In the case of a flux, this again is meters. The units of this whole integral are flux, so the units of F in this case are flux per meter. All right, general conclusion you should obtain from this slide is that a field that only has a circulation component has no flux, and a field that only has a flux component has no circulation. So you might say that these two are orthogonal to each other, two orthogonal properties. All right, so let's actually now, instead of choosing a contour that's centered on the origin, let's put it at some arbitrary position and let's repeat this calculation one more time. So in this case, the position vector is basically a circle centered on x0 and y0. And again, we're going around the circle, so nothing has changed. It's just moving this circle to different locations on the xy plane. If I now compute the tangent vector and the normal vector, this constant term disappears. So the tangent vector and normal vectors are still the same, irrespective of where basically the center of the contour exists. However, in computing the circulation, we're basically computing F at the position, which means here now we do have to introduce the location. So if we compute this now, you do the integral, first the dot product followed by the integral, you still end up with 2 pi r squared for this particular case. So nothing has changed. We moved it to another location and we still end up with the same answer. On the other hand, with flux, we go through the same calculation procedure. The only thing that changes is we're evaluating F circle at the position x0, y0, and so of course this changes, but we still end up with 0. Redo the calculations for circulation and flux, assuming that the field is the flux field, and again we end up with no differences. So in this particular example, which is not going to be generally the case, but for this particular example, the circulation and flux are not impacted by the location at which the computation is performed. All right, so that's sort of interesting. So let's go one step further now. We'd like this value that we've computed to be independent of the area of the region enclosed by the contour. So the simplest thing is divide through by the area, which was pi r squared. If you do this for the various cases that we considered, right? So there's f circ TDS, f flux TDS, f circ NDS, f flux at NDS. Then the only thing that's left is the value of 2 here, 0, 0, and 2. All right, so conclusion is that normalization, dividing through by the enclosed area, allows us to make circulation and flux independent of the contour chosen. I like the notion of making it independent. It's some intrinsic property of the field that we basically are now looking at. Okay, but we've taken a simple example. Can we now generalize this to something a little bit more sort of complicated? In other words, we don't have to have circular contours. We can have other things. In fact, what we'd like to do is to sort of watch what happens if the contour is made smaller and smaller, vanishingly small, such that the area becomes very small. And so effectively what we're doing is we're enclosing a contour around a given small point in space. So this is basically going to be a limiting process. All right, that means we're going to reformulate the normalization process, but we're going to consider a differential area. So let's consider a differential area where the contour shrinks down so that it encircles a single point, which we call a limiting process. And now we define the properties of the vector field at a given point on the xy plane by its divergence and its curl. So now we're introducing the notion of these two different properties, right? The divergence implies that a source, a flux density, a vector field, is producing a field, either a source where the field lines diverge from a point, or a sink where field lines converge to a point. So lines can be going outwards or going inwards. The divergence word comes from the fact is lines diverging, meaning they basically are all moving outwards from a given point. Convergence would mean converging to a single point. Curl implies an axis of rotation and a magnitude of a circulation density. So when we looked at, for instance, a contour, a field that was basically forming a closed contour, forming a circle, all right? How do you describe the properties of a field that's moving in a circle? Well, we normally would associate that with an axis of rotation. Okay, so an axis of rotation basically would sort of give you some sense as to that it's moving about something, and that something is an axis. And you then would ask the question, well, what is the direction of this axis? Well, this is where the right-hand rule comes into play. We're going to use a right-handed coordinate system convention. So if the contour is traversed in a counterclockwise direction, and the following applies, and I've given you a couple of options. So the direction of the field and the direction of right-hand fingers point in the same direction as the contour traversal. If that's the case, then the direction of the axis of rotation is in the positive z direction. On the other hand, if it's an opposite direction as the contour traversal, then the direction of axis of rotation is the minus z direction. The field on average has the same direction as the contour traversal, right? In that case, the direction of axis of rotation is in the plus z direction. If the field on average has the opposite direction as the contour traversal, then the direction of axis of rotation is the minus z direction. All right, so now this brings a bit of a conundrum because we're dealing with a 2D problem. How can we talk about an axis of rotation being in the z direction when we've restricted ourselves to a problem in which it's a 2D problem? Okay, we'll refer to this issue later, but let's say for now that this axis of rotation in 2D is going to be called a pseudovector. It's a pseudovector because we cannot explain it in any other way. It has the properties of vector, but clearly it doesn't exist in 2D. Anyway, we'll be coming to this shortly in a subsequent lecture. Okay, so next step is basically we're going to go and look at the formulation of the divergence in 2D. We're going to look at the formulation of a curl in 2D and formulation of divergence in 3D and the formulation of curl in 3D. So we're going to look at all these four different cases. starting with the 2D divergence formulation. And so this is now going to be a definition. The divergence in 2D, this is how we explain it. This is an operation performed on a vector field. And this basically is going to be a scalar. It looks like a dot product, but we'll show what this looks like really shortly. It's on the right. This basically says we're taking a calculation of flux around a closed contour and dividing by the area bounded by that contour and letting that area go to zero. That is the formal definition, a limiting process. The units for F are going to be flux per meter, and the units for the divergence of F are going to be flux per meter squared. The divergence operator, what does that mean? That just means that we're taking the delta, which is like the gradient operator, which would have partial x, partial y, and we're having this operate in a dot product fashion on the vector field F, which means the fx component fy. So if we basically apply this as we would a dot product, then this partial derivative of x operates on fx, and this partial derivative of y operates on fy. And because this is additive, then this becomes df partial x dx plus df partial y partial y. All right, so how do we set this problem up? Well, this integral that you see here is basically what we're trying to do. So we're going to take a little square like this one. This is the area. And we're going to go around the contour in a counterclockwise direction. And this represents the direction vectors that are normal to the contour. The field vector basically is shown here as a field vector, different field vectors that we're looking at in this problem here. So for instance, since it's involving a dot product, the only field vectors of interest are field vectors are parallel to the direction in which we're operating. So for instance, if we're moving along this line, then any field component that's normal makes no contribution to the dot product. So the only field that's of importance when we integrate along this direction would be the field x. But the value of the field here and the value of the field here will be different. So you'll notice here, y hasn't changed. F of x at this point and f of x are different. So this one differs by x plus dx. If this is x, then this point here is x plus dx. We can do the same thing with y. If we're moving in this contour, only the fy contributes. So here we'll be evaluating at y plus dy, whereas here we're evaluating at y. X hasn't changed, so the x is the same in both cases. So this side and this side basically represent fy's. This side and this side represent fx's. And so now what we have to do is just to compute this over the 4 line segments. And that's more or less is what I've done here. Okay, there are 4 line segments, 1, 2, 3, 4. But I've grouped these so that I've got the x's together and the fy's together. If you basically go through this calculation here, right, then you have f of x plus dxy minus fxy dy. Yeah, but what is this? And divide it by dx in the limit, right, because it's a limiting process. That's df partial dx. But you have a dy on top and a dy on the bottom, and they cancel out. Similarly on this side, this would be a dfy partial y, but you have dx on top and dx on the bottom, so they cancel out. So the final result is this. So this is nothing more than a proof. This is a proof to show that this calculation, in fact, gives you this result. This is how you actually do the calculation, but this is where the formal definition comes from. And by the way, this is again just showing that because we're dealing with discrete lines, in other words, going around the contour is not a continuous process, and we have to break this up into 4 different line segments. And so, again, this is just a review of what we mean by f.nds, and recall what nsds is. It's basically a description as shown here. So this is the 2D formulation, divergence formulation. All right, we've done the computation of the divergence for 2D. We're now going to consider the case for 3D. In other words, the formulation of the 3D divergence formula. So the picture that we're using here is going to be different because the definition in 3D for divergence involves integrating the flux over a closed surface. And that's basically the expression that you see here, divided by the volume enclosed by the surface. And the surface here basically consists of 6 discrete surfaces forming a square-like object. And so we need to know the directions of the field and also the directions of normals to the surfaces. There being 6 surfaces, you can see there are going to be 6 orientation vectors. So one back surface, this bottom surface are reference surfaces, so that would be with respect to x's, y, and z. So for example, the bottom surface here, right, this has an orientation vector pointing downwards. This is with reference to z, this is NSZ. This vector, which is on the top surface, right, it's pointing upwards, but it's equal at position z plus dz. This vector would be at position y, whereas this position would be at y plus dy. Back vector would be at sx, and the forward one would be at x plus dx, right here, x plus dx. So these are basically the normals to the surfaces. Similarly with the field vectors, here basically we will be evaluating on the back surface in the y direction, x, y, z. Here we'd be evaluating at y plus dy. Now the only field vectors we're interested in are the field vectors which are parallel to the surface area vectors. So for this one and this one here, it's Fy. For this one and this one here, it's Fz. And for this one and this one, it's Fx. It's the only ones of interest to us. All right, so the units of F are flux per meter squared, and units to divergence of F will be flux per meters cubed. Now, what does this symbol divergence F mean? It basically means that I'm taking the gradient operator. In this case, it's 3-dimensional, so it's partial x, partial y, partial z. And it operates on the vector field, x component fx, y component fy, z component fz. And so you treat this like a dot product, but this ends up being this operating on this operating on this, and this operating on that. If you do that, you end up with this expression, which represents the divergence of the vector field F. And this is classically the type of computation we would be doing if you're asked to compute the divergence of a vector field F. So now what we're going to basically do is we're going to do this calculation here, and we're going to prove that in fact this is represented by this, okay? And so that means we have to take each one of these 6 surfaces and compute the flux on each surface. And that's basically what I've done. So for instance, in the x direction, there's the back surface and the front surface. So you'll see an x plus dx and an x, right? And this is in the x direction because we're only interested in that component which is parallel to the normal to that surface. So there's this surface and that surface, which is a combination of these 2 terms, right? And then we have for the y, which is the back surface here and the back surface here, which are these 2 terms that you see here. And the top surface and the bottom surface, which are these 2 terms that you see here. Now, if you look at this calculation, you'll notice that fx state plus dx, and this is minus fx of x, divided by dx. But that, by definition, in the limit is the partial derivative of f of x with respect to x, leaving dy dz as being common to the numerator and denominator, so they can cancel out. Here, and that's this term, here, it's y that's being perturbed. It's y plus dy, and here it's y minus divided by dy in the limit. This is just going to be dfy dy. Why? Because the dx dz and the dx dz numerator and denominator will cancel. And the last one would be where z is preserved, z plus dz minus fz divided by dz. That's dfz by partial dz. And notice that the dx and the dy terms are common to numerator and denominator, and so they basically disappear as well. And so we've just proven that this relationship is correct, and this comes from the definition of the divergence of a vector field F. This just shows how things were broken down into 6 individual integrals, and that represents all the 6 terms that you see here. If you want to know what the area vectors are, then for example here, this is n for the z plus dz term. That z plus dz would put you this vector. Well, it's pointing in the z hat direction, all right? And sure enough, it is. And the differential area with respect to the xy plane, dx dy. This one basically is z, which would be the lower surface. right? But the lower surface has a vector pointing in the opposite direction, in the minus z hat direction. So this vector would be 0, 0, minus 1 dx dy. Now you can go through all the other cases to show, in fact, these results are correct. And then all you're doing is just substituting these values into these expressions along with the values of x evaluated at the given surface. And that's how we arrived at these 6 terms that you see here. All right, now let's look at the curl formulation. And so the first thing to do is to look at 2D curl formulation. So here basically what we're interested in looking at is circulation. All right, and the circulation effectively, by definition, we already had discussed, is that we take the contour integration of the field and the tangent vector, right, around a closed contour and divide by the area enclosed. So in this case, basically, we're going to take the xy plane. We're going to put a contour here. Here it is in the counterclockwise direction. And according to the right-hand rule, the area vector would be pointing out of the page, which being in the z-hat direction. That's why I show z here. Now, of course, you can't perform a curl operation or any form of cross-product in 2D. And so we're assuming that the z direction exists. And so this basically then is the final result you would get if you were to look at the z component of the curl operating on the vector field f. But by definition, this would be just this formula that you see here. Units for f would be circulation per meter, and the units of the curl of f would be circulation per meter squared. Okay, so let's basically do this calculation, and what we want to show is in fact that this isn't equal to this. And so down below I've shown how that's done. Here is what we start with. We're going to let the area go to 0. And again, you'll notice here that the only field components we care about are the ones which are tangent to the contour. So along this contour here, we only care about f of x. Along this contour, only about fy. Along this contour, fx. Along this contour, fy. At this point here, the field is f of xy, of 0. Whereas at this point here, this is a little bit further on. So this will be when we move in this direction along here. This is at a value of x plus dx that you can see here, and then a function of y. When we get to this point, then basically y is held constant. We're not changing, but this is at y plus dy, and x is allowed to vary. Along this section here, basically, we know basically that at this point x and y is held fixed, and so we can see that we end up with a result here that's fxy 0. Okay, so we have now all the 3 vector fields of interest, and we're going to be taking a dot product between this one and this one, this one and this one, this one and this one, and this one and this one, taking into account directions. Okay, so we've shown the fields basically pointing this way and this field pointing this way. All right, so let's basically do it for each one of those contours. So the first one basically would be f partial y. So that would mean these 2 components, this one and this one. And if you look at this is f of y, x plus dx, whereas this one here, the dot product of the 2, they're in opposite directions, so you get a minus sign showing up here. In this case here, we're looking at this and this. In this case, we're looking at y plus dy, so we're looking along this direction. This will involve a minus because they're in opposite directions. And this one and this one, they're in the same direction, but I put the minus outside, so if you take minus times minus, this would be positive. And we're dividing by the area, which is dx dy, because it's in the xy plane. Well, if you look at this, then you can see this must be the derivative of fy with respect to y partial, and dx basically, in this case, the y becomes common to numerator and denominator, so it can be cancelled out, and that gives you then the first term. The second term has a minus, and then y plus dy here and y here. So this is dfx by dfy with a minus. X is common to numerator and denominator, so they cancel out. So you end up with this expression. Well, this is in fact what we just started out to prove. So this is equal to that. We've just proven that to be the case. And what did I do? I basically computed the circulation, components of circulation around the closed loop. And there were 4 segments, so 4 individual integrals. And this is just to recall that ft dot t ds is fx dx plus fy dy. And recall that TdS is x dot y dot dt, or in explicit form dx dy. Okay, so the last thing now is to look at the 3D curl formulation. In the 3D curl formulation, we know it's a vector that points in the x, y, and z direction. And so what we do is we set up three different circulation intervals, one in the xy plane, one in the zx plane, and one in the zy plane. So I've chosen to do the details for the case where we're set up a contour in the zy plane. And in all these three cases, we basically satisfy the right-hand rule, which means that the contours are always going to be in a counterclockwise direction. And the circulation vector, which basically is the axis of rotation, must be pointing according to the right-hand rule. So if you basically look at the circulation here, it's take your right hand, the thumb will be pointing out of the page, which would be, in fact, in the x-hat direction. That means our coordinate system is consistent with right-hand convention. Here, we have the z-axis pointing here, the x-axis pointing here. Again, it has to be counterclockwise. If we now apply right-hand rule, we'd be pointing out of the page, which is in the y-hat direction, which is consistent with the right hand. And here, we have x pointing this way, y pointing this way. This is counterclockwise. Again, the right hand, the thumb points out of the page, which is in the z-hat direction, which is consistent with the right-hand rule. So all the three diagrams are set up properly. And so now we basically, all we're trying to do is to do this computation, followed by this computation, followed by this computation. And so x subscript just means that this is the component of the axis rotation in the x direction. This would be component of the axis rotation in the y direction, component of axis rotation in the z direction. So this looks very similar to what we just did for the 2D formulation. So we'll just go through one more time, but we'll have to do it, you'd have to do it two additional times, once here and once here. You can leave that as an exercise to yourselves, but we're basically just doing it for this case here. Okay, so we're just going to prove that, and so that means we need to take the closed loop integral of f dot ts, divide by the area bounded, and that's just ax hat that you see here. And again, we need to break this closed loop integral into four different segments. Why? Because this is not a continuous contour. And the only field vectors we're interested in are the ones which are parallel to the tangent vectors for each side of the contour. So along this contour, we only care about the fy component. Along this contour, only the z component. On this side, the y component. On this side, the z component. Again, we're basically evaluating the field at this point. And this point basically would be fxyz. If we're looking at along here, then we're looking at the fz component, but evaluated at y plus dy, which is here. So it doesn't change along here. Y remains constant at y plus dy. When we move along here, then we're looking at value of z plus dz, but we're going to be evaluating along the y direction. And similarly on this one, we'll have x, y, z. And so we set this integral up. You'll notice that the dot product between this and this will be negative. Between this and this positive, between this on this side here and this side here will be positive, and this side will be negative. So we have two negatives and two positives. So if you look down here, this is basically now the calculation we've done. You have f of z at y plus dy, which is this one. The tangent vector is in the same direction, so it's positive. Then on the other side, you have the tangent vector in this direction, but the field in this direction. But so it's a minus sign. If you look at this, you see it's y plus dy minus y divided by dy. So that's the partial derivative of z with respect to y, which is the term that you see here. Similarly, by the way, the dz is common to numerator and denominator, so they cancel out. For the second term, you can go through the same procedure. In this case, it's z plus dz on one side and z on the other side. In one case, they're in the opposite direction, the tangent vector and the field vector. In the bottom case, the field and the tangent in the same direction. So you get a positive contribution to the integral here and a negative contribution to an integral here. And so effectively, we end up with this expression that you see here. So this is z plus dz minus z dz. That's fy partial with respect to z. And dy is common to numerator and denominators. That cancels out, and you're left with minus this term here. So minus is here, the minus is there. So this now is consistent with that, and so we've proven everything's correct. Again, the details of this for the case of the x component of the curl, basically I've shown here that this is just the sum of the contributions of the four sides. This is what we mean by the closed loop integral. Again, by definition, f dot des is fy dy plus fz dz. And recall this would be the explanation or for TDS. This would be in the parameterized case, and this would be in the explicit case. Well, that concludes Lecture 21A. Thank you for listening.